Welcome back to Introduction to Chemical Engineering. In this short video, I'm going to give you a little bit more detail about what we're going to cover in the chemistry module. So as a reminder, we're going to start with the products, and this for the chemistry is fuel or camera, sensors, film. We're going to look at the chemistry involved in these products, and which includes fuel, film, and the role of the engineer. What does the engineer have to know? What does the engineer do to make these products feasible? So we're talking about chemistry. What is going to be in the chemistry module? And the two products we're going to talk about in the chemistry module are fuel and light and camera sensors. Okay, so chemistry, the chemistry of gasoline. What is gasoline? I mean, gasoline is a mixture of hydrocarbons, as they call chemical compounds made of hydrogen and carbon. And there's a way in which you introduce oxygen, you can make it burn, and that creates energy, and in turn creates other molecules, and then creates also the mechanical energy to move automobiles. So we'll talk a little bit about the combustion process when it comes to gasoline. The concept, some of the things we'll look at in the chemistry module is things like balancing of chemical reactions. What happens if you burn gasoline of a certain composition, oxygen? What are the products? How can you calculate how much energy you might get? What is the difference between, say, burning methane versus butane versus propane, for example? What is the typical compositions of the gasoline that we can use to, say, calculate how much energy we might get if it burns with 100% efficiency, so on and so forth. So we will look at chemical reactions. We'll look at the balancing of the chemical reactions. We will take a look at the calculation of the energy released from these chemical reactions. We will also take a look at why it is necessary to burn the fuel completely and totally, or total combustion versus incomplete combustion. And there is a difference in the amount of energy that we get per unit, say, weight of gasoline. We'll take a look briefly at the difference between gasoline and diesel. And some of you might know the difference already. A diesel engine does not need a spark plug in order for the fuel to actually burn. In the diesel engine, when you mix diesel vapor with hot air, for example, and then you compress them, it'll actually ignite by itself. Unlike a gasoline engine, which actually requires a spark, a source of a spark to ignite it. So we'll take a look at the difference in the properties of the gasoline and diesel engine. And then we'll ask the question, where does gasoline and diesel come from? From the typically, when you get most of the gasoline and diesel from crude oil. And then crude oil is distilled. You heat the crude oil, creates vapors, and then you condense the vapors in a distillation column. We'll talk about that. And you collect fractions of the crude oil. One of the fractions is gasoline, another fraction is diesel. There are other fractions, of course, also including aviation fuel, so on and so forth. But the basic process is called distillation. And another important operation for chemical engineering is fluid catalytic cracking. So you can take large hydrocarbons and break it up into smaller hydrocarbons, because in gasoline and diesel actually typically contains smaller hydrocarbons. By that I mean C10, C12, C14, those kind of molecules. So if you have a very large hydrocarbon, you can use a method called fluid catalytic cracking to break it up into the more valuable products with gasoline and diesel. So that's an important unit operation. So as I mentioned, we'll talk a little bit about the difference in the fuels and how the energy of combustion, for example, gets converted to mechanical energy. And then we'll talk a little bit about, essentially, is one thing to write an equation, calculate the amount of energy it releases, and so forth. But the key is that if you just have something just burning in the open air, for example, it is impossible to capture that energy. What happens in a gasoline and diesel engine is that it's actually, the combustion happens in a confined chamber. And the liquid gasoline is converted to vapor, combusted, creates additional vapors, and increase the pressure in this internal chamber causes essentially a lot for the car to move. So we'll talk a little bit about the combustion process, understanding the relationship between combustion, the energy, the mechanical energy that it actually creates, and so forth. So we'll write equations that have fuel on the left-hand side of oxygen. We'll write balanced equations allowing us to calculate essentially how much of energy is released from combustion. And then we'll take a look at briefly about gas laws, as it were. Is there a way to understand the relationship between pressure, volume, and temperature, for example, in the internal combustion engine? Just quickly, without a lot of detail. So the concepts, we're going to be looking at a balancing of chemical reactions. We're going to take a look at complete or incomplete combustion and the energy change to the chemical reaction. We'll take a look briefly about the difference between gasoline and diesel. As I said, this one is the gasoline engine, this one is the diesel engine. We'll briefly take a look at what contributes to the difference in the properties of these two fuels. Okay, and then we'll take, as I mentioned, the engineer. The engineer's role is to manufacture these fuels, gasoline and diesel, from crude oil. And this is just a picture of refineries. If you drive along Interstate 10 in Louisiana, Texas, for example, you'll see these big columns all making gasoline and diesel from crude oil using the process of distillation. We'll talk a little bit about that. And here's a good figure of a distillation column, and you can actually see there are different fractions actually all the way from very heavy hydrocarbons in the bottom to very the lighter material right at the top with different cuts, as it were, from the column. In the chemistry portion of it, we're going to look at sensors. And as I mentioned, we're going to look at silver halides and CMOS CCD sensors. The chemistry concepts you're going to look at involve things like understanding photon sensitivities, how light impacts molecules and how that is important in the electronic properties of molecules. And in the engineering portion of it, you're going to ask, how does an engineer use these light-sensitive materials? How does an engineer make them? What are some of the things an engineer has to do in order to make these materials for use in cameras and sensors and so forth? So we'll talk about a little bit about CMOS, complementary metal oxide semiconductors, CCD arrays, PMTs, and so forth. And then there are some good images of these things. You can see the silver halide films here and the digital camera type films on the right side. The question is, what is the role of the engineer in making these films? Typically, it's like, for example, silver halide films, you need to be able to control the emulsion size and distribution. And then for the solid state sensors to control the material properties by appropriate doping and other processes that actually done. So there's a lot of engineering involved in making these materials, and because they had to be manufactured very precise specifications. So in the chemistry modules, we're going to talk about fuel, we're going to talk about cameras, in particular the sensors using the cameras. And we'll take a look at some of the chemistry concepts that the engineer needs to understand as part of the making the fuel using these films and so forth.